So as we know, the magnetic dipole moment of a current carrying loop is equal to M equals to I into A. So M is the magnetic dipole moment, I is the current, A is the area of the loop. If you consider this loop, then let's say A is the radius, then A, what will be A? It will be pi A square, is the area of this circular loop. So we can change this M equals to I into A, and A is pi A square. From there we get I equals to M pi A square. So I will get the current in terms of magnetic dipole moment divided by area. Now we know the magnetic field at the center of a current carrying loop is mu naught I by 2A. So if you have a this current carrying loop, so what is the magnetic field at the center? This we have already derived it. So that is equals to mu naught I by 2A. So you should remember these formulas, okay? All the formulas which you have found in your previous class to find the magnetic field, you should remember it because this is good for the numerical purpose. So B equals to mu naught I by 2A. Okay, so you replace I by this formula, which is which finally we will get this equals to this. Okay, if you replace I by this, then we'll get this. So here we get the magnetic field at the center in terms of dipole moment. So this is one of the general formulas. You can sometimes they ask you to derive this also. Okay, so this is important. If you have a, so this is the formula when of the magnetic dipole moment for a single loop. If you have an n number of loops, n number of current carrying coils, okay, if you have n number of turns, then the magnetic dipole moment will simply be n into Ia. Now we'll find the magnetic dipole moment for a revolving electron. Sometimes they ask this question, find the magnetic dipole moment of a electron in the hydrogen orbit. It's the same thing because in the hydrogen orbit also it has one electron, no? So see, this is the orbit of the electron, and the electron is revolving around this orbit anticlockwise in anticlockwise direction. Okay, and the current is flowing opposite to this. So this is like this. Again, you have to use this. So this is the velocity of the electron. This is the radius or the position of the electron from the center. Okay. Now, if the angular momentum is asked, what is the direction of the angular momentum? If you have not heard the term angular momentum, then see, just like linear momentum is represented by P, which is equals to mb. No, if any particle is revolving, then it has angular momentum, and the direction of the angular momentum is represented by this thumb. If this is direction of the electron moving, particle moving, then this thumb will show the direction of the angular momentum, which is this z, which is represented by the z. Okay, since electron is moving in the anticlockwise, thumb would show in the upward direction. This is the direction of the angular momentum, and opposite direction of the angular momentum is the direction of the dipole moment. Okay, this is the direction of the dipole moment. So we have an electron which is moving with velocity. We have an electron of mass me, of charge minus e, and moving with speed v in a circular orbit of radius r. So then the current would be what? Current is formula is q by t, charge is e. Okay, we just use the magnitude over here. We have not written the negative sign. We are just concerned about the magnitude. Therefore I equals to e by t. E is the charge of the electron and t is the time. Okay, that is the formula. T is the time period. Time period means the time taken by the electron to make a complete round. Okay, so I equals to e by t. T is the time period. So how can we find time period? We know velocity equals to distance by time. Okay, so velocity equals to distance by time. What is distance over here? Distance is 2 pi r. And what is the time for 2 pi r? The time for 2 pi r equals to capital T, one time period. Therefore we can say velocity equals to 2 pi r by t. Therefore t equals to 2 pi r by v. So we get t equals to 2 pi r by v. Okay, velocity equals to distance 2 pi r by t. Therefore t equals to 2 pi r by v. Okay, if we replace t over here, then we get I equals to this value. Okay, and we got I. We want to know the magnetic dipole moment. So we know m equals to I into A. I we got. A also we have to find. A is pi r square. Obviously A is pi r square. So you get m equals to EVR by 2. This is equation 1. Now angular momentum of the electron. Since the electron is revolving, okay, around a point, we also have to find the angular momentum. Angular momentum is represented by Z, okay. Z equals to mvr. This is the formula. For if it is linear momentum, then the formula would be just m into v. If it is angular momentum, there's one more term which is multiplied, which is r. R is the distance of the particle, revolving particle, from the center around which it is revolving. So this is r, okay. So Z equals to mvr, which is equation 2. Now we divide this equation by this equation. So m by Z equals to, we get m by Z equals to E by 2me. So m is the dipole moment here, Z is the angular moment here. So finally we write m vector equals to, we will take this to this side, E by 2me into Z. So this is the final expression for the magnetic dipole moment in terms of orbital angular momentum of an electron which is revolving, okay. So this expression is also important. Sometimes they ask the derivation for this.